Section 10.4, Objective. I can use the relationship between logarithmic and exponential functions. Remember that we have the function f of x equals 2 to the x, and if we graph that function, we use these ordered pairs to graph it, and we get this graph. F of x equals 2 to the x is this red line. Well, since this graph passes the horizontal line test, we know that there has to be an inverse of this function. And so we know that by switching the ordered pairs, f inverse of x has to have the ordered pairs 1/4 -2, 1/2 -1, 1 0, 2 1, and 4 2. So if we plot those points, so 1/4 -2 is right here, 1/2 -1 about right there, 1 0, 2 1, and 4 2, so that the inverse function is going to be a graph that looks something like this. So this is f inverse of x. Well, these inverse functions are what we call log functions. So f inverse of x is what we call log base 2 of x. Okay? This is a logarithmic function. So a logarithmic function is the inverse of the exponential function. This is the exponential function, and this is the inverse, the logarithmic function. The way that we read this notation, so log base 2 of x. So log base 2 of x is how we read that. And again, a log is just the inverse of the exponential function, okay? So if I have something in exponential form, so for instance, 2 cubed equals 8, okay? Well, 2 is our base, 3 is the exponent, and 8 is the actual value. Okay? So to put that into log form, log is short for logarithmic, okay? Then it's log base, and notice the base is kind of a subscript, a little bit below base, of the value equals the exponent. Okay, so the inverse would be log base 2 of 8 equals 3. So notice that a log is always equal to the exponent from exponential form. Okay? The subscript is the base from exponential form, and the value, which is on the same level as the log, notice the 2 is like a subscript, the value is the value of the base to that power. Okay? So if I was going to take the log form 5 squared, well, 5 squared equals 25, and I want to change that to log form, so it's going to be log base 5 of the value, which is 25, equals the exponent. Okay? So remember that this is the base, this is the exponent, and this is the value. Okay, so if I had 2 to the 5th equals 32, then in log form, that would be log base 2 of 32 equals 5. So again, notice that it's always equal to the exponent, okay? So in general, okay, definition. If b and n are positive numbers with b not equal to 1, then log base b of n has to equal to k if and only if b to the k equals n. Notice that from the definition, b and n are positive numbers. That's a really important thing. So the base and the value always have to be positive. Okay? And so we have some properties of logs. So if we have log base b of m equals log base b of n, that's only true if and only if m equals n. Okay? So, for instance, log base 2 of 16 is equal to log base 2 of 4 times 4. Okay? Well, that is true because 16 equals 4 times 4. Okay? Next one. Log base b of b to the k equals k. Since if you put it back into exponent form, we have b to the k, so the base to the power equals the value. Okay? So in number form, if I have log base 5 of 5 cubed, that has to equal 3. Because if I take it out of log form and put it into exponent form, the base to the power has to equal the value. So 5 to the third has to equal 5 to the third. Okay? Number 3. So that was 2, this is 3. Log base b of b equals 1. Since b to the 1 equals b. Okay? So log base 6 of 6 equals 1. So notice that when the base and the value are the same, it's always going to equal 1. And that's because if you take it out of log form and put it in exponent form, 6 to the 1 equals 6. Okay? And number 4, another really important one, log base b of 1 equals 0. Since b to the 0 equals 1. So with numbers, log base 8 of 1 has to equal 0, since in exponent form 8 to the 0 equals 1. Okay? And then the last one, number 5, b to the log base b of n has to equal n. Okay, so notice, You have a base, and then you have a log with the same base. Then that has to equal, the value. Okay, because again, if you take it out of log form and put it into, this is an exponent form, and you put it into log form, it's going to be log of the base, this is the base, of the value equals, this is the value, equals the exponent. Okay? So, example. We want to be able to go back and forth. So number 1, express log base 3 of 81 equals 4 in exponent form. Right? So right now it's in log form, so I want to put it back into exponent form. So 3 is the base, 4 is the exponent, and 81 is the value. So this is exponent form. Number 2, express 5 cubed equals 125 in log form. So this is exponent form, so I want to change it to log form. So it's log of the base is 5, of the value, which is 125, equals the exponent. Okay. Now, we also want to be able to what's called evaluate logs. In other words, what is the log equal to? Okay, so evaluate. Log base 2 of 125, of 0.125. Okay. So what we want to know is 2 to what power equals 0.125. All right, so first of all, we set it equal to x because we don't know what its value is. We want to know what its value is. Then we take it out of log form and put it into exponential form. So it's 2 to the x equals 0.125. Now we want to, this is a decimal, so we want to change it into a fraction. So it's 3 decimal places, so we can change it into a fraction by writing it with a 1 and 3 zeros. Okay. And then we can break that down. So this is 2 to the x, and 125 goes into 1,000 8 times. So that's 1 over 8 if we reduce that. Okay? Now, remember when we have the variable as an exponent, we want to get the same base. So we can change this to 8 to the negative 1, but 8 is really 2 cubed. Right, and now that our bases are the same, we just set the exponents equal. So x has to equal negative 3. So the value of log base 2 of 0.125 equals negative 3. Okay, since 2 to the negative 3 equals 0.125. Okay. Number 4. Evaluate log base 1/9 of the 4th root of 3. Okay, so in other words, we want to know what is that log equal to. Well, we don't know that, so we let that be x. Then the next thing is take it out of log form and put it into exponent form. So we get 1/9 to the x equals the 4th root of 3. Okay, now change everything into exponent form. So I'm going to write this as 9 to the negative 1 to the x equals 3 to the 1/4, because remember this radical can be written as a 1/4 power. Now we notice that this is a 3 and this is a 9. But 9 is the same thing as 3 squared, so we can rewrite it that way. Okay, so we get 3 to the negative 2x, because we multiply all these together, equals 3 to the 1/4. Now that our bases are the same, now we can set the exponents equal. So we take negative 2x, set it equal to 1/4. So I can multiply by negative 1/2. So I get x equals negative 1/8. So log base 1/9 of the 4th root of 3 is exactly equal to negative 1/8. That is the value of that log. Okay, number 5. Now this one says solve because notice that it's already set equal to x. Okay, so you don't have to do it yourself as we did in the previous two columns, or previous two problems. That's why this one says solve as opposed to evaluate, because it's already set up as an equation. So, but you do the same process. Take it out of log form, put it into exponent form. Try to get the same base. Then set the exponents equal. Okay, so the solution is 1/2. Okay, and the last one, again, it says solve because it's already set up as an equation for you. But in this case, we're looking for, we're looking for the base, but the process is still the same. If it's in log form, take it out of log form and put it in exponent form. So it's x to the negative 1 equals 5. So then we want to make this into a 1, so we multiply it by negative 1. So we have to do this by negative 1. So we get x equals 5 to the negative 1, or x equals 1/5. So our solution is 1/5.